Hi, and welcome to the APA webinar, Hurricanes, Earthquakes, and Tornadoes, Wood Designed for Extreme Forces. I'm Brian Redling, professional engineer with APA, and I've been observing damage due to extreme wind events for the past 20-plus years. Today, we will discuss important considerations for design and construction of wood frame buildings to resist these extreme wind events. To begin, APA was formed in 1933 as the Douglas Fir Plywood Association. In the 1960s, the name changed to American Plywood Association to reflect the use of southern pine in the production of plywood. As a nonprofit trade organization, APA now represents over 156 member mills in the U.S. and Canada, manufacturing a variety of engineered wood products. The name was changed again in the early 90s to APA, the Engineered Wood Association, to more accurately reflect the new product mix and a new geographic range, both the U.S. and Canada. Products include plywood, oriented strand board, wood I-joist, glulam timber, structural composite lumber, and many associated products. Also, technical information and recommendations discussed in this webinar can be accessed through APA's Designer Circle for free, a part of the APA website at apawood.org. Please sign up for the Designer Circle to obtain access to our extensive library of technical literature, as well as to receive regular newsletters from APA concerning changes to building codes and design technologies. So today our outline includes wind and seismic forces and cost-effective systems for resisting these forces. Some tornado myths: load path, where continuity in the load path is the key element, wall bracing, shear walls, and diaphragms, and there's really something for everyone here in this program. Builders, designers, and code officials will have important take-home messages from this webinar. So to begin, the basis for both the loads and the resistance is found in the International Building Code. And increasingly, the Building Code refers to outside documents such as Wood Frame Construction Manual, the National Design Specification, and APA literature for detailed information on these various topics. One such reference is American Society of Civil Engineers, ASCE 7, Minimum Design Loads for Buildings and Other Structures. Another code reference document is the National Design Specification by American Wood Council. The NDS provides resistance information for both wood materials and connections used within a wood assembly. The American Wood Council also publishes the special design provisions for wind and seismic, which takes into account specific technologies for resisting lateral forces. Provisions for wood members, fasteners, and assemblies commonly used for resisting wind and seismic forces, using both allowable stress and load factor resistance methods for analysis, are included. This publication is free for download at American Wood Council website at awc.org. The special design provisions was referenced in the 2006 IBC but became mandatory in the 2009 IBC. So some of the changes that were brought about in the 2008 include the ability to design for combined shear and uplift using wood structural panels, provisions for determining capacity of unblocked shear walls, two-sided shear walls. Also, a shear capacity adjustment factor equation was added to the perforated shear wall method, increased strength limit for perforated shear walls, and changes to the high-load diaphragm accommodation. So, the Wood Frame Construction Manual is another publication by AWC and is a handy reference for both prescriptive and engineering solutions to common design scenarios that are encountered in wood frame construction. Supplemental to the Wood Frame Construction Manual are the guides to wood frame construction in high wind areas. There are separate documents shown here address wind design requirements in 90, 100, 110, 120, and 130 mile per hour exposure B wind zones. For other wind speeds and exposures, you can simply refer to the 2012 Wood Frame Construction Manual. But these separate guides are based on the provision contained in the wood frame construction manual and are the reference document for high wind wood frame construction in the IRC. Use of the high wind provisions in these guides will result in design solutions that are prescriptively meeting the requirements of the wood frame construction manual and the IRC. The prescriptive design of buildings in high wind regions is also addressed in ICC 600, formerly SSTD 10, and it gives a cookbook approach to design of smaller, more simply shaped buildings. An important distinction should be made between prescriptive construction and engineered design, where prescriptive bracing is called for in the International Residential Code with limits to the building size and wind speeds. But these are braced wall panels and not to be confused with shear walls. Without hold downs, this is the main difference between brace wall panels and shear walls, that the brace wall panels do not require the use of hold downs. So for prescriptive design, wind speeds over 100 miles an hour, refer to the wood frame construction manual or the ICC 600 document. Many contemporary home designs offer less opportunities for traditional wall bracing due to an abundance of windows and doors, especially in the front and rear elevations. In addition to bracing methods given in the residential code, an APA simplified bracing method presented by this System Report 102 gives more versatile solutions by offering the ability to use thicker panels at a tighter nailing schedule above the code minimums. And what this does is allow for narrower bracing segments to be used. It gives more flexibility in accommodating the greater amounts of openings as found in contemporary home designs. As with all APA publications, SR 102 is free for download at apawood.org. The special report SR 102 takes into account an added effectiveness of continuous wall sheathing as represented in the IRC wall bracing method CSWSP, or continuously sheathed wood structural panel, and thereby gives partial credit for walls that are otherwise too narrow to be counted as a bracing unit. The effect of continuous sheathing can be seen in buildings such as this, where integration of the building is achieved in 3 dimensions. These continuously sheathed walls form a much stronger elements, a box, essentially, to resist the lateral forces. In this case, storm surge from Hurricane Katrina pushed the building off of its foundation, but yet it held together by the continuous exterior sheathing or skin of the building. The weak link here, obviously, is at the load path connection of the base of the wood frame portion to the foundation. We'll talk about that later in the program. The recent publication by APA, Building for High Wind Resistance and Light Frame Wood Construction, offers a low-cost system that can be applied to IRC-compliant construction and prescriptively reinforces minimum IRC construction in the weak links that have been identified in some of the high wind events. These have been common in standard wood frame buildings. So it's a 9-point checklist of time-tested details that seek to better provide wind resistance by reinforcing the common vulnerabilities in prescriptively built homes. Remember that the IRC is not a design, does not provide a design to resist a specific load, but is a cookbook measure. But by applying these high wind resistant details, a low cost, as little as $600 on a 2,100 square foot home was estimated as the cost of applying these options to a single-story ranch average size home. And it also offers a benchmark for which prescriptive buildings can be constructed to a Code Plus level or above the code minimums, whereby resistance to wind can be dramatically increased for really a small expense. This will be an attractive option for builders who wish to differentiate their homes as safer and more damage resistant than those constructed to code minimums. In contrast, engineered buildings as defined by the International Building Code must include a rational analysis to provide a complete load path for both vertical and lateral forces. In wood construction, the uplift and lateral load paths are less obvious, so empirical methods, or those based on testing, have been developed to allow a departure from a more rational approach. However, the skin or exterior wall sheathing serves as a valuable structural role and provide continuity in the uplift and lateral load path system. So here wind forces are simply determined by multiplying the wind pressure, both positive and negative, to the area of the building over which the wind force pressure acts. Our lateral load systems for resisting the loads include rectangular plates, also known as shear walls, and floor and roof diaphragms that give the structure the ability to resist racking forces and to carry the forces to the foundation and eventually to the ground. Shear walls and diaphragms are simply constructed of framing members sheathed with wood structural panels with enough nails so that the parallel framing represented by the wall and roof assemblies remain rectangular. Another important aspect to building performance is that the walls and roof elements are connected together and to the foundation adequately so that they do not become separated from each other or the foundation in an extreme load event. Resistance to both positive and negative pressure is required for adequate building performance. Negative pressure may result in uplift as it applies to this roof. Positive pressure exerted on the windward wall here may also be exerted on the interior of the building should a breach in the building envelope occur in the area of positive pressure. This is often due to flying debris and loss of window and doors from flying debris and wind pressure. And when a breach occurs, the interior of the building can suddenly become pressurized, adding to the uplift and lateral forces already being exerted on the exterior surface of the building. Seismic or earthquake forces are exerted on the building due to acceleration of the ground. However, the building doesn't know a lot of difference as far as it's the same assembly that resists the seismic force as does the wind. The difference is that the force is generated from the ground acceleration, whereby the building is left to catch up with the foundation movement, accelerating and decelerating in 3 directions simultaneously. Lateral and uplift forces are determined by the product of the building mass times the ground acceleration. So the greater the mass of a building, the greater the lateral force for a given seismic acceleration. An easy way to visualize seismic forces is to imagine forces exerted on this building due to starting and stopping curves and bumps in the road that will cause this dwelling to undergo acceleration in 3 directions at the same time. Wood frame buildings have a long proven track record of good performance in seismic events such as this home, subjected to the Good Friday earthquake in Anchorage, Alaska in the 1960s, the largest seismic event ever recorded in North America. Although directly located on a fault line, this home remained intact. Wood buildings are light and flexible, resulting in lower seismic forces to be resisted. Remember that the force is equal to the mass times the acceleration. So lower mass equals a lower force. And the redundancy in the system, which uses thousands of nailed connections within a building such as this, results in good performance because of the energy absorbing qualities and the stiffness in resisting the elements. So both energy dissipation and reduced lateral force and redundancy allow the wood systems common in North America to perform well if properly constructed. What about tornadoes? A common misconception is that tornado forces are too great to expect buildings to survive. So indeed, extreme events such as this F5 tornado offer little hope for a building survival, but with winds in excess of 300 miles per hour, the forces are beyond realistic resistance level for most structures. This is often given as an excuse for minimal wind-resistant detailing, though, in some tornado-prone areas. The incorrect assumption is that tornado forces are too extreme for ordinary buildings to resist. This would be true if all tornadoes were rated EF5, or the 300 mile per hour plus variety. Here we see the enhanced Fujita scale indicating a wide range of wind speeds associated with tornadoes EF0 through EF5. Generally, these tornadoes are classified based on descriptions of the damage. So, you know, it's a judgment call many times by the observer as to which rating a tornado might be given. This table communicates the percentage of occurrence for various EF tornado ratings, and you'll notice that the percentage is weighted towards the lower end of the scale, where EF0 through EF2 represent a cumulative of almost 96% of all tornadoes, and the higher wind speed EF3 through 5, smaller, less than 5% of the overall tornadoes that are measured each year. So we can see the EF2 and below. These are wind speeds that we're already accustomed to designing for in high wind hurricane areas. So there are a few facts here that we should recognize is that 90% of all tornadoes are EF2 and below. 70% are less than 110 miles per hour. And the damaging winds in a given tornado outside the vortex are many times slower than the maximum rating of the tornado. Unrealistic to protect against EF4 through 3, 4, and 5 tornadoes, but we can provide recommendations to protect the building shell in the lower rated wind speeds, including almost 95% of all tornadoes. This image reflects a variation in wind speed along the path of the tornado affecting Tuscaloosa, Alabama in the super outbreak of 2011. A team of engineers and scientists closely observed damage within the circled area of the tornado path as it traveled close to the University of Alabama. And you can see within the circled study area, a detailed study was indicated a variation in intensity from F0 through F4 within this area. As you can see, within the damage area, more of the area can be attributed to the lighter EF0 and EF1 winds than the more extreme events located sporadically along the vortex. Data collected along a small segment of the tornado path indicate the greatest area was EF0 through EF2, with a small percentage in the EF3, EF4 range. Much of the damage attributed to the lower wind speeds could have been resisted using the details covered in the APA High Wind Guide. This list of time-tested details has been compiled in the APA publication shown here, offering improved continuity and reinforcement to common areas of vulnerability in wood frame buildings. For a small increase in cost, buildings can be constructed and offer dramatic improvements in resistance and wind forces. The first detail addressed in the publication is roof sheathing attachment. It's recognized that improvements can be made by using more nails. 4 and 6 nail schedule shown here versus the code minimum 6 and 12. For attachment of roof sheathing panels to the framing. Doubling the number of nails, in this case, effectively doubles the resistance to the uplift pressure on the roof. Further enhancement can be accomplished using deformed shank nails such as ring or spiral shank nails for improved pullout. Here, roof sheathing loss at the gable-end overhang is in a relatively light tornado wind could have been resisted by a few more nails. In this case, there's a slight departure from the panel edge nailing requirements since really what we want is the higher capacity 4-inch on center nail spacing to occur at the last gable-end framing, not at the effectively at the panel edge, which occurs at the non-structural barge rafter at the end of the overhang. Some deformed shank nails are specifically intended for use where increased capacity is desired. In this case, a larger head may be incorporated for enhanced pull-through resistance. Another real-world challenge is when step-down trusses are used in hip roofs. In this case, the roof sheathing is sloped, but the nailing surface of the truss top chord is not. This invites poor connection between the two. A better detail for framing this area is to use purlins on top of the step-down hip trusses so that the nailing surface is flush with the roof sheathing, and the direction of the roof sheathing does not need to change. Common vulnerabilities are observed at gable ends. The triangular gable end wall section is often poorly connected to the building along the top and bottom edges of the gable end. Poor connections to the bonus room floor and garage ceiling at this location results in lateral instability at the gable end, originating from a hinge forming at the top of the gable end wall. This detail is recommended for alleviating the problem by tying the gable end walls back to the structure and eliminating the hinge point at the ceiling and second floor framing elevation. Here, a strap is used in conjunction with 2x4 lateral braces at 6 feet on center. Here's another example of where gable end is found to be weak link in the building resistance to a relatively strong tornado EF3 approximately. Pressure requirements for wind acting on the exterior surface of a building are specified in the International Residential Code. These are localized pressures referred to as component and cladding loads that are meant to be resisted by the siding and wall sheathing in the home's exterior. These minimum pressure requirements apply to all residential buildings constructed according to the IRC. Specific component and cladding loads can be accommodated using APA's TT 105 Technical Topics Report Requirements for Wall Coverings and Wind Pressure, available for download at the website. Table 1 from this publication gives specific nailing required to resist the component and cladding loads in the IRC, but a more general approach represented in the high wind guide will be to use more nails for attachment of wall sheathing than is required by the code. This is especially important along the gable ends where no interior gypsum is present on the inside face of the wall to assist in resisting the wall pressure. Here's two examples from Hurricane Katrina that show the effect of poorly attached non-structural sheathing to the gable ends of homes. Large amounts of water infiltration have resulted in massive loss to the home's interior and contents in this neighborhood. Uplift forces due to negative wind pressure on the roof in this diagram must be continuously carried to the foundation. In this example, the weak link appears to be the connection of the walls to the foundation. More common weakness is at the roof-to-wall connection, where toenails are still allowed in some cases for the connection of roof rafters to supporting walls. The roof system shown here, flipped upside down, was vulnerable to due to the relatively low resistance of the nails used here, otherwise known as toenails, which have a relatively low resistance to pull out or withdraw from the top of the wall. A better way to accomplish this critical connection is to use a light gauge metal connector as illustrated from this figure from the APA High Wind Guide. These diamond-shaped connectors offer resistance to load in all three directions, both uplift and the two horizontal directions. In this case, the nails are not pulled out by the load, but the nail is loaded perpendicular to the shank, which is much stronger. Another useful piece of hardware are structural screws that can be added to enhance the roof-to-wall connection. These can be combined with metal connectors in cases where the connectors don't offer enough capacity, or used alone as an enhancement over code minimum toenailing. Traditional uses for wood structural panel wall sheathing include the resistance to shear in the wall system to resist racking. Another efficient use of the wall sheathing is to resist uplift. In most cases, the wall sheathing can be purposefully designed to bridge across discontinuities in the wall framing to resist uplift forces simultaneous to shear resistance, as can be seen in this photo, where discontinuity in the floor system is being tied together by the OSB wall sheathing. As represented in APA Tech Note E510, this method for handling uplift loads across structural discontinuity is a very efficient method and can reduce cost and construction time as compared to the use of metal connectors across joints in the wall framing, such as you see here. Many wall sheathing manufacturers are now making oversized panels, and these are longer than the standard 8-foot panels, still 4 feet wide, intended for wall applications where the panels extend from the sill plate to the upper level band joist. These are manufactured intentionally for 8, 9, and 10-foot walls, typically eliminating mid-height blocking, allowing easy inspection of the continuity of the load path. Studies of this taller wall sheathing indicate that less air infiltration results and a more direct uplift lateral load path is obviously a benefit here. Of course, when there's only a small segment of wall between two openings, the use of metal connectors will still sometimes be needed. There may not be enough wall between the two openings to accommodate. There are two methods for using wood structural panels to provide uplift resistance. The first involves the uplift tension being transferred by the studs where the horizontal joints are located away from the discontinuities of the framing. In this case, additional nails can be placed in the studs to accommodate the uplift at this location. This is usually easy to accomplish since additional nails can fit easily along the intermediate framing members, where most fastening schedules for shear wall attachment require only 12-inch on center fasteners at the interior or at the intermediate wall framing members. The other method outlined in APA E510 allows the splice to occur at the rim board, where uplift fasteners are placed in the rim board at the splice. Of course, this requires that the rim board be designed for vertical force, which is perpendicular to the rim board length. It's not possible with rim board using lumber or other products without design capacities in the vertical or short dimension. However, APA plywood and OSB rim board, such as these used in conjunction with I-joist floor systems, are acceptable for this application due to their significant strength that's available perpendicular to the member length. The APA High Wind Guide also recommends prescriptively sheathing all walls continuously, above and below the openings. This offers great strength improvements over prescriptively braced minimum wall bracing. And as we shall see, even with the loss of wall coverings and house wraps, continuous plywood and OSB sheathing offer additional protection. Examples of good building performance of recently constructed homes were observed after the 2011 super outbreak, such as these homes in Pleasant Grove, Alabama. Although mostly stripped of wall and roof coverings, these homes offer safety to occupants from the violent tornado forces due to the strong shell provided by the wood structural panel continuous wall sheathing on these fully sheathed homes. Another photo from this subdivision illustrates the degree to which tornado forces affected the region. Note the trees and vegetation in the background. Trees stripped of small limbs, and fence posts here are stripped of the fence boards, but the building's shell remains intact through good detailing. Even in cases where a siding is destroyed, such as with this fiber cement siding, wood structural panel wall sheathing offers good protection for the home's interior from wind and water and flying debris, which is often included in the wind field. As compared to homes prescriptively braced according to the IRC, such as this one that I observed in Wilson, North Carolina, corner braced with OSB with a non-structural sheathing infill. Here wind resistance is much less than with a fully sheathed home. Note the vegetation around this home, almost unaffected by the winds. Let's take a closer look at this building and note the corner bracing from the right front corner of the home still lying in the front yard. Here's the corner bracing unit, still relatively intact but no longer a part of the home. On the other side of the home, we see a section of the exterior wall completely removed between the corner bracing and a T intersection with the interior wall. Also note the gable end in this photo, as it's almost completely stripped of siding and non-structural sheathing. This home is likely not compliant with the IRC, since these wall assemblies almost certainly do not satisfy the component and cladding pressures listed in the IRC. Also note the doghouse here is still intact, fully sheathed with plywood. Another important detail in the APA High Wind Guide shows the wall sheathing overlapped with the bottom plate or foundation sill plate, allowing direct nailed attachment to the foundation anchorage. In this example from Raleigh, North Carolina, all of the essential elements are in place, but the load path is not continuous due to poor nailing at the bottom of the exterior wall sheathing in the region of the foundation. We can see from this vantage point that the wall sheathing nails at the bottom were mainly located along the rim board instead of the sill plate, and there are too few nails. Another common occurrence observed in tornadoes are due to breaches in relatively light gauge garage doors that cover relatively large openings. So the larger the opening, the more wind can affect the building's internal pressurization. Here, the loss of the garage doors pushed the sidewalls out and the roof up. Taking a closer look at the wall on the left-hand side we see that the garage sidewall was poorly connected to the sill plate, with very few fasteners observed along the bottom of the wall sheathing into the sill plate. Rotation at the bottom plate was also observed, indicating a partial failure of the bottom plate connection to the foundation. Due to relatively large uplift forces at this location, APA recommends larger plate washers spaced 48 inches on center at this location as an upgrade to code minimum requirements in the IRC. Larger 3x3 plate washers, relatively inexpensive, are much more effective at holding down the bottom plate as compared to minimally sized round washers typical in this installation. Slided plate washers are a common piece of hardware in seismic areas where they're required in high seismic prescriptive construction. This connection is limited by the steeled wood bearing area, where crushing of the bottom plate material is likely in determining the overall capacity of this connection. Better uplift resistance is offered by the larger washer shown on the right, as it incorporates more of the plate material below the nut on this anchor bolt. In this image, we see that the larger plate washer increases the bearing area of the anchor bolt, but also, since the washer incorporates nails from the bottom of the wall sheathing, cross-grain bending in the bottom plate material, which is a potential failure mode, is also reduced. Testing in APA labs using larger plate washers at the bottom of walls subjected to uplift and shear simultaneously confirms this assertion. This home damaged in May 2011 tornado due to poor foundation anchorage. And note the vegetation around the home, relatively intact, an indication that the wind forces were relatively light in this wind event. Despite the moderate winds, the home has shifted approximately 6 feet from the original location, and the garage is totally collapsed. Closer observation revealed no anchor bolts, and the sill plates in this case were poorly attached to the foundation, using steel pins that were easily pulled out of the foundation material. Similar conditions were observed in newly constructed homes in harder hit areas of Alabama, as in this case, where exterior walls are largely absent from this home, constructed atop a slab-on-grade foundation. We can see that the bottom plate's absent from the perimeter of the slab, adjacent to the glued-down hardwood flooring. But upon closer examination, we see that an attempt was made to nail the plates to the perimeter of the slab, and the head of this fastener pulled through the bottom plate. In other cases, the nails were observed to be bent below the bottom plate, did not penetrate concrete foundation. This photo shows the result, taken in the same neighborhood, and shows a completely stripped home, all of the framing removed from the foundation by the wind. APA System Report SR101 gives more detailed information and design guidance for walls subjected to combined uplift and shear. This apparatus in the APA lab confirmed the values that are recommended for the spacing of foundation anchor bolts, as well as the methodology for using wall sheathing to resist simultaneous shear and uplift forces. Methodology is also reflected in American Wood Council's special design provisions for wind and seismic. APA full-scale testing of uplift at the bottom plate connection confirmed these connections eliminate cross-grain bending or splitting of the bottom plate, as well as confirming the allowable uplift capacities given in Table 1 of SR102. This test report is available for your review at apawood.org. In this figure, we're looking at the horizontal roof diaphragm in plan view, with the wind force applied along the windward edge of the roof sheathing and being distributed out to the shear walls parallel to the load, otherwise known as shear walls or wall bracing in the case of a prescriptively constructed building. With adequate attachment of the wood structural panel roof sheathing to the wall framing, this roof element, known as the roof diaphragm, will remain rectangular and serve to distribute the loads to the resisting walls without excessive deflection or failure. So it's the roof sheathing that keeps this assembly rectangular through adequate attachment. This type of analysis resembles that of a simple span beam, where the beam would be located from top to bottom, simply spanning between the resisting walls. The bottom of this deep beam is subjected to tension forces just like a normal beam, which is normally resolved by tension splices in the top plate of the leeward wall. Shear within this beam analogy is assumed to be carried in the web and is designed through seismic or through selection of adequate fastening in the roof sheathing to the framing to resist these racking forces. In the case of sloped roofs, the designer can conservatively assume that the roof is flat for analysis purposes. Analyzing it as a flat roof, even if it is sloped, will result in a conservative design. There are two scenarios for design of horizontal diaphragms, roof and floor diaphragms, and that is unblocked and blocked diaphragms. Here we see unblocked diaphragms where the edges perpendicular to the floor framing or roof framing has a lower design capacity as compared to the blocked diaphragm shown here, where all the panel edges are attached to a common framing member. Blocked diaphragms are stiffer than unblocked diaphragms and offer greater design capacity for resisting applied forces, as lateral forces are more easily and readily transferred within this system. Shear walls are normally assumed to be blocked, but the 2008 special design provisions for wind and seismic for the first time gives designers an adjustment factor for use in unblocked shear walls. This pertains to shear capacity adjustments for walls up to 16 feet in height based on cyclic testing of assemblies with as much as a 2-to-1, as small as a 2-to-1 aspect ratio. Designers have two choices for horizontal diaphragm analysis, the flexible or rigid. The designer will normally have either method from which to choose, and depending on the building configuration, these two idealized assumptions offer differing but adequate results. So for flexible diaphragms, it's considered a scenario where the deflection of the diaphragm is greater than twice that of the shear walls. In this case, the load is distributed to the shear walls by a tributary area. Diaphragm acts like a series of simply supported beams. With the rigid analysis, where the deflection defined as where the deflection of the diaphragm is less than twice that of the shear wall, the diaphragm load is distributed to the shear walls by the wall stiffness, where a torsion can be incorporated in the design. This gives more flexibility for shear wall layout in many cases, but it offers a more complicated analysis. The only case where the code is clear on which method should be used is where there's cantilever diaphragms or open-ended buildings, where rigid analysis is required to take into account the eccentricity between the load and resistance to load. So let's look at some examples. Let's assume this is our building layout with two exterior resisting walls, one interior. With a flexible analysis, the load is distributed according to the tributary area, and so the distribution is half the load to the middle wall and a quarter of the load to the exterior walls, compared to a rigid analysis where the load is distributed according to the stiffness of the resisting elements or shear walls. And so in this case, all the walls have the same stiffness and carry a third of the load. Changing that up slightly, reducing the stiffness of the interior wall, this case results in the interior wall half as stiff, so it receives only 20% of the load, and 40% of the load goes to the exterior walls. So in comparing the two methods, we see that with the flexible analysis, even with the short wall in the interior portion, we would end up with 50% of our load in this location. And with the rigid analysis, only 20%. This may be more compatible with our building design. So it's up to the designer, again, to use whichever analysis method is more appropriate, but the only time where it's mandated is for cantilevered diaphragms in open-ended buildings. But rigid analysis allows the designer to take into account the torsion resulting from an eccentricity that exists between the load and the resistance to the load. In this case, the torsion is resolved by distributing additional load to the perimeter shear walls. A challenge that is encountered is the transfer of the roof diaphragm loads to the top of the resisting shear walls. In this case, an interruption in the load path is often encountered where racking of the framing members in this area may represent a disconnect in shear transfer from the roof to the walls. So some type of blocking or X-bridging would be needed in this area to resolve the discontinuity. The 2012 IRC weighs in on this subject by requiring blocking to be placed between the framing when the distance from the roof sheathing and the top of the wall exceeds 9.5 inches. This shows the roof sheathing and blocking installed to eliminate the overturning failure of the roof and the ceiling framing in this area. Overturning must also be considered in the design of shear walls, where hold-down anchors at the base of the walls resist the overturning force. As a result of hold-down anchors, they are appropriate at the stop and start of each shear wall segment. In this photo, the hold-down anchor is connected to the vertical stud pack at the limit of the shear wall element. The hold-down is different than the anchor bolt in that its job is intended to resist uplift, where the anchor bolt is intended to resist uplift and sliding forces at the base of the wall. The hold-down anchor is intended to resist overturning. Anchor bolts are ineffective for providing hold-down forces, since the distribution of load along the base of the wall in this case will result in an unzipping of the wall sheathing from the bottom plate. The hold-down anchor, in comparison, results in an equal distribution of force to the fasteners along the vertical stud element. Hold-down anchors such as this one, intended for seismic forces, where, in seismic events, the rounding of the base of the traditional hold-down connector can lead to excessive deformation. The rounded base on this connector eliminates this problem, as do the screwed connections shown here, a tighter connection with less slip, which is important in the seismic performance of buildings. This photo shows a hold-down connector commonly used in multi-story applications, where shrinkage in the framing after construction can lead to slackness in the overturning resistance of the connection. So a self-tightening mechanism shown here alleviates this problem. It's often encountered in taller wood frame buildings. From there, the force is transferred by a continuously threaded rod with couplers to the foundation. Also shown are large timbers adjacent to the hold-down, often used instead of multiple studs to accommodate overturning compression forces, which can be significant at this location. Also seen here is a structural composite lumber bottom plate, which offers higher compression stresses available perpendicular to the bottom plate. The building code allows the designer to use up to 60% of the design dead load to resist overturning of the shear walls due to wind and seismic forces. The remainder of the force must be resisted by the overturning connectors. Shear wall capacity is affected by numerous properties, including the specific stud species, the APA wood structural panel grade and thickness. Thicker panels result in higher shear wall capacities up to 5/8 inch thick. Thicker panels from there do not improve performance, as the capacities are limited by the individual fastener, really just limited by the fastener performance at this point. Also, specific nail size and spacing affects the capacity. More nails at the perimeter of the wall sheathing gives more capacity. Additional nails along intermediate framing members do not affect the capacity in any significant way. A caution here is for designers in the eastern U.S. to stay away from the structural 1 grades, which are primarily available for design of high seismically loaded diaphragms on the West Coast. Stay with the common rated sheathing product values instead of the structural 1 grades, which primarily are available in high seismic areas. For design of walls to resist loads, the minimum aspect ratio for a shear wall is limited to 3.5 to 1 for wind and 2.5 or 2 to 1 for seismic. The aspect ratio is simply the height to width ratio. An exception is made for seismic design where 3.5 to 1 ratios can be used with a penalty determined by the multiplication of 2 times the width over the height. Starting with the 2006 IBC, a 40% increase was allowed in the shear wall and diaphragm tables for wind resistance. The code authors agreed that the 2.0 factor of safety was appropriate for wind resistance due to a higher degree of certainty with regard to the loads as compared to seismic. Also for wind design, adding capacities of dissimilar materials is allowed. Designers may now add the capacity of gypsum sheathing on the interior side of the shear walls for wind resistance only. So a comparison of wind and seismic analysis shows a disparity in capacities for the same wall due to these factors. That the wind is 40% increase for design of wind, of the tabulated values. The gypsum strength can be added, a smaller aspect ratio. If we perform an analysis of this arrangement, we have a 3.5 to 1 aspect ratio with a 3 and 12 nail spacing, 8D nails with gypsum on the opposite face of a 7/16 with structural panel wall sheathing. So to determine the wind resistance to this assembly, we take the tabulated value 450 times 1.4 for the 40% increase. The gypsum capacity of 100 pounds per linear foot is added for a total of 1,640 pounds total for this 2.25 length wall. For seismic, we have no increase to the tabulated value, no gypsum capacity added. We actually take a reduction since it's not a 2 to 1 aspect ratio. This results in a number of much less capacity, only 570 pounds per linear foot for seismic resistance of the same wall. How about using adhesives? Well, adhesives can improve shear wall strength. It's theoretically possible, although you would need to use a rigid adhesive, which is not appropriate for field applications where variability and quality control is difficult to achieve a known adhesive capacity. So it's not advisable to combine an adhesive with nails to increase the stiffness or strength of a shear wall. With the adhesive connection being stiffer than the nailed connection, the adhesive must fail before the nails can receive the load. This is not allowed practice, especially in high seismic zone, where the practice can lead to catastrophic and sudden failures. Site-built portal frames are an option when shear wall aspect ratios or minimum bracing widths in prescriptive construction are not met. Here, extra lateral resistance is offered by a moment connection at the base of the narrow walls, and a moment resistance is also achieved through a lapping of the wall sheathing at the top of the wall with the extended header, which extends to the outer limits of the narrow wall segment. Design of portal frames for engineered applications is outlined in APA report TT100. A similar method is used for prescriptively designed wall bracing. That's the portal frame without hold downs. This is referred to as a bracing method, CSPF, continuously sheathed portal frame, in the IRC, and is similar to the engineered portal frame except without hold downs at the base. For more information on the narrow wall bracing method shown here, you can refer to the IRC or APA publication J740. So there are 3 primary methods for shear wall design available to the designer: the segmented, force transfer method, and the perforated method. Traditional segmented approach assumes that openings in the wall due to windows and doors is an interruption in the system, and so the shear wall is limited only to full height segments adjacent to the openings. In this case, hold downs would be necessary on each end of each shear wall segment. The force transfer method is simply an exercise in statics using free body diagrams of separate rectangles making up the wall system. Then the mechanical connections, such as the metal straps shown here, are used to transfer forces between the rectangular elements. Probably the most designer-friendly method for shear wall design where multiple openings are present is the perforated method that counts for openings in the wall system based on testing. Advantages for this method are that it's simple and hold downs are only needed at each end of each shear wall line. Reductions in strength of an otherwise uninterrupted shear wall are accounted for by a shear capacity adjustment factor. It should be recognized that reducing hold down anchorage generally has an effect of reducing cost on a given building design, as compared to the traditional segmented approach to shear wall design. The force transfer method and the perforated methods generally give more economical solutions by reducing the number of hold downs. So let's take a look at these three systems individually, starting with the traditional segmented approach. In this case, only the full height segments are considered to be part of the shear wall system. Shear is distributed to these full height segments based on their length, with each segment being designed to resist the overturning forces independently. As mentioned previously, this may result in an abundance of hold-down anchors in wall systems with numerous openings using the traditional segmented approach. The main advantage to the force transfer method is that the height-to-width ratio is determined by the wall pier, or the light-colored segment adjacent to the openings in this figure. And so it can result in a much narrower segment adjacent to the openings, since the height-to-width ratio only applies to the wall pier. Again, the shear around the openings is based on a rational analysis accounted for by strapping and framing. Hold downs are only required at the ends, but this is more of a calculation or design-intensive method with added construction details for the connections. The shear wall perforated method makes the assumption that the shear wall includes partial height segments, and a reduction is taken in the overall shear capacity through the use of a shear capacity adjustment factor, which is determined based on the height of the openings and the percentage of the wall that's contains full height sheathing, meeting the governing height-to-width ratios. In this method, hold downs are only required at the ends of the shear wall line, and so a reduction in the number of shear walls hold downs is likely. With the 2008 special design provisions for wind and seismic, this method, formerly limited to 490 pounds a linear foot, has been expanded to include higher limits, 980 for seismic and 1370 pounds per linear foot for wind. The shear capacity adjustment factor generally is determined using this table from the special design provisions for wind and seismic, where the percent of full height wall sheathing and the maximum height of the opening is cross-referenced to give a reduction factor to be applied to the base value of the wall capacity, as if it had no opening. More recently, an equation has been added to more precisely estimate the shear capacity adjustment factor. The equation takes into account the actual area of openings in the wall as compared to the table that assumes all openings are the same size as the maximum opening size. And this allows for more precise and efficient designs using the perforated shear wall method. A few of the publications that will assist in your design include the APA diaphragm and shear wall literature, which gives numerous design examples, APA's SR102 simplified wall bracing method for prescriptive construction, and APA's building for high wind resistance, also intended for prescriptive construction, all available for free download at the website apawood.org. A sampling of additional resources of interest may include the Engineered Wood Construction Guide, E30, Roof Fastening for Wind Uplift, Shear Transfer at Engineered Wood Floors, and Roof Retrofitting for High Wind Uplift. Also, these technical topics on issues such as fastener performance are also available for free download. For any questions concerning the topics discussed in this webinar, you are welcome to contact me or the APA Help Desk at the email and telephone number listed. Thank you for attending the APA webinar.